Where does this moment go when it ends? You are reading these words in what feels like the present, a thin sliver of time that seems to be the only thing that truly exists. Behind you sits the past, apparently gone. Ahead lies the future, apparently not yet real. This is how nearly everyone experiences time, as a single moving point that converts an open future into a fixed past, one instant at a time. But physics may tell a different story. According to one serious interpretation of relativity, the past has not vanished at all. Yesterday still exists. So does the morning you were born. So does every breath you have ever taken. They are not memories stored in your brain or echoes fading into nothing. They are real locations in the structure of the universe, no less actual than the chair you are sitting in right now. This idea has a name. It is called Eternalism, sometimes described through the model of the block universe, and it emerges directly from the mathematics that Einstein used to describe space and time. If it is correct, then the flow of time you feel so strongly is a kind of illusion, and reality is something far stranger and far more permanent than it appears. Over the course of this video, we will examine the evidence for this view, the experiments that support it, and the deep questions it raises about memory, death, and the nature of now. We will treat it not as fantasy, but as a hypothesis built from established science. The conclusion may unsettle you. The reasoning behind it is harder to dismiss than you might expect. To understand why anyone would seriously propose that the past still exists, we have to begin with something deceptively simple, something you experience constantly without ever questioning it. We have to begin with the present moment itself. Right now feels special. It feels like the only time that is genuinely real. The words you read a moment ago are already slipping into the category we call the past, and the words you're about to read sit in the category we call the future, not yet arrived. Between them lies this razor-thin edge we call now, and it appears to be the only place where anything actually happens. The past seems to be a kind of fading record, real once but no longer, while the future seems to be pure potential, a set of possibilities that have not yet been selected. This is the intuitive picture almost every human being carries through life, and it is so deeply built into the way we think that questioning it feels almost absurd. Yet when scientists and philosophers look closely at this picture, it begins to dissolve in their hands. The first problem is that the present moment, the now we treat as the foundation of reality, turns out to be extraordinarily difficult to define. Ask yourself how long the present lasts. Is it a second? That cannot be right, because within that second, there is an earlier part that has already passed, and a later part that has not yet come. Is it a tenth of a second, a hundredth, a thousandth? No matter how small a slice you choose, you can always divide it further into a before and an after, and the genuine present seems to shrink toward a duration of zero. But a moment with no duration at all is a strange thing to build a universe on. If the present has no extension in time, how can anything happen in it? Motion, change, thought, all of these require some passage of time, yet the present we cling to seems to have none to offer. This is not merely wordplay. It points to something that physicists noticed long ago, which is that the laws describing how the world behaves do not contain a special moment called now. Write down the equations that govern a falling apple, an orbiting planet, a swinging pendulum, or a beam of light, and you will find variables for position, for velocity, for mass, for time itself. But nowhere in those equations is there a marker that says this particular value of time is the present, and all the others are either dead or unborn. The equations treat every moment in exactly the same way. To the mathematics, the instant of your birth and the instant of your death are simply two values of a variable, equally specified, equally real, with no flag attached to either one declaring it to be happening now. The now that feels so vivid and so central to your experience is completely absent from the fundamental description of nature. Consider how peculiar this is. Almost everything else you experience has some counterpart in physics. The warmth of sunlight corresponds to the energy carried by photons. The pitch of a sound corresponds to the frequency of a pressure wave. The color red corresponds to a particular wavelength of light. Again and again, the things we feel and perceive turn out to map onto measurable quantities in the physical world. But the passage of time, the sense that the present is sliding forward and dragging us with it, has no such counterpart. There is no term in any equation that captures the movement of now, from one instant to the next. Physicists can describe the relationships between events at different times with extraordinary precision, but the flowing, the becoming, the sense that the future is steadily turning into the past, simply does not appear. Some have tried to dismiss this as a limitation of our current theories, a gap that future physics will eventually fill. But the gap has not closed. It has widened. As our understanding of time has deepened over the past century, the special status of the present has become harder to defend, not easier. The more carefully we examine the structure of reality, the more it seems that the division into past, present, and future is not a feature of the universe, but a feature of us, of the particular way conscious beings process the world. And this raises an immediate and difficult question. If the now is not out there in the physics, then where is it? Why do we feel it so strongly? Part of the answer lies in how the brain works, and we will return to that in detail later. For now, it is enough to notice that your sense of the present is built from a great deal of processing. Light reflecting off objects takes time to reach your eyes. The signals from your retina take time to travel to your brain. Your brain then takes time to assemble those signals into a coherent scene. By the time you consciously experience this moment, the light that carries it left the page or screen a fraction of a second ago, and the neural events underlying your awareness are already over. The now you experience is, in a precise sense, slightly out of date. It is a reconstruction stitched together from information that arrived at different times and was processed at different speeds. The brain smooths over these delays so seamlessly that we never notice them, presenting us with the comforting illusion of a single, unified instant. This already suggests that the present is at least partly a construction, rather than a simple given. But the deeper challenge to our ordinary view of time does not come from neuroscience. It comes from physics, and specifically from the discovery that the present moment is not even something different observers can agree on. We tend to assume that there is a single universal now spreading across the entire universe, a cosmic instant that everyone everywhere shares. We imagine that at this very second, whatever is happening on a distant planet is happening now, simultaneously with our own experience. This assumption feels so obvious that it hardly seems worth stating. Yet it is precisely this assumption that the science of the last century has overturned, and its collapse is the doorway through which the strange idea of eternalism enters. Before we walk through that doorway, it helps to sit for a moment with how radical the situation already is. We have a present moment that we cannot define without it shrinking to nothing. We have fundamental laws that contain no trace of that present and treat all moments as equally real. We have a brain that manufactures the feeling of now from delayed and reassembled information. Each of these on its own might be set aside as a curiosity. Together, they begin to suggest that the entire framework of a moving present, a vanishing past, and an open future may be a story we tell ourselves rather than a description of how things actually are. There is a useful way to picture the alternative, though we will develop it much more carefully later. Imagine a long strip of film, the old-fashioned kind made of many individual frames. Each frame is a complete still image, frozen and unchanging. When the film runs through a projector, the frames flash by quickly enough that we perceive smooth motion, a story unfolding in time. But the motion is in the viewing, not in the film. The film itself is just a long sequence of static frames, all of them equally present on the reel, the ending as physically real as the beginning, even while you're watching the middle. Eternalism proposes that the universe is something like that strip of film. Every moment is a frame that exists permanently, and the sense of the film running, of one frame giving way to the next, is added by the viewer rather than contained in the reel. If that comparison is even roughly accurate, then the implications are staggering. It would mean that the moment of your 10th birthday is still there on the reel, exactly as real as this moment, simply located at a different point along the strip. It would mean that nothing is ever truly lost, because nothing ever truly stops existing. It would also mean that the future is already present on the reel, waiting in frames we have not yet reached, which would force us to rethink everything we believe about choice, possibility, and chance. These are extraordinary claims, and they should not be accepted lightly. A serious investigation has to ask whether there is any real evidence for them, or whether the film analogy is just an appealing picture with nothing solid behind it. The remarkable thing, the thing that makes this topic worth taking seriously rather than dismissing as speculation, is that the evidence does exist, and it comes from one of the most thoroughly tested theories in the history of science. The argument does not begin with metaphysics or wishful thinking. It begins with measurements, with clocks and light, and the behavior of objects moving at high speed, all confirmed in laboratories and verified by technologies we use every day. To see how a strip of film could be a serious model of reality, we have to understand what happens to time when things move, and what Einstein discovered when he asked a question that seemed almost childishly simple. What would the world look like if you could chase a beam of light? The answer would tear apart the universal, now that everyone had taken for granted, and in its place leave something far harder to imagine. The question that unraveled the universal present was not framed as an attack on time at all. It came from a young man in his 20s, working as a clerk in a Swiss patent office, turning over a puzzle that had nothing obviously to do with the nature of reality. Albert Einstein was thinking about light, and about a contradiction that had been quietly troubling physics for decades. On one side stood the equations describing electricity and magnetism, worked out by James Clerk Maxwell, which predicted that light travels at a specific fixed speed. On the other side stood the ordinary common sense of motion, the kind we use without thinking, every time we watch one car overtake another on a highway. These two pictures could not both be fully correct, and the place where they collided turned out to be the foundation of everything we believe about the present moment. To feel the contradiction, imagine you are standing beside a road and a car passes you at a steady speed. Now imagine a second car chasing the first, moving faster, gradually closing the gap. From inside the second car, the first car appears to be moving slowly because you are catching up to it. The relative speed between you is small, even though both cars are moving quickly relative to the road. This is how velocities combine in everyday life. If you run forward on a moving train, your speed relative to the ground is the train's speed plus your own. Speeds simply add and subtract depending on how observers are moving. Nothing about this seems controversial. It is the arithmetic of motion we absorb as children and never question. Now replace the car ahead with a beam of light. According to Maxwell's equations, light moves through empty space at one particular speed, an enormous figure, but a definite one. The natural assumption, the one that flows from the highway picture, is that if you chase the beam fast enough, it should appear to slow down relative to you, just as the first car did. Chase it hard enough, and perhaps you could come alongside it, watching the light wave hang frozen beside you, like spray suspended above a wave, at the moment a surfer matches its speed. Einstein, as a teenager, had wondered exactly this. What would a beam of light look like if you traveled alongside it at its own speed? And the more he examined the physics, the more impossible the frozen beam became. Maxwell's equations did not allow for stationary light. A light wave that was not moving was not a light wave at all. Something had to give. The resolution Einstein arrived at was as bold as it was simple to state. The speed of light, he proposed, is the same for every observer, no matter how that observer is moving. It does not matter whether you are standing still, racing toward the source of the light, or fleeing from it. You will always measure light moving at exactly the same speed. The chasing car can close the gap on another car, but no amount of chasing will let you close the gap on a beam of light. It outruns you by the same margin whether you sit still or pursue it with everything you have. This single assertion, that the speed of light is constant for everyone, is the seed from which the entire revolution grows. At first glance, it sounds like a minor technical fact about light, the sort of thing that might interest engineers, but should have no bearing on the deep structure of time. But hold the idea up to the light of everyday reasoning, and it begins to crack the world open. Speed is distance divided by time. If two observers moving differently both measure the same beam of light to have the same speed, and yet they are moving relative to one another, then something about their measurements of distance and time cannot match. The arithmetic forces it. If the speed comes out identical for both, but they disagree about how fast they are moving relative to the light, then they must disagree about the distances and the durations involved. In other words, to keep the speed of light constant for everyone, space and time themselves have to bend, stretch, and shift, depending on how each observer moves. Time was no longer the fixed, universal backdrop everyone had assumed. It became flexible, personal, tied to motion. The consequences arrive quickly, and they are deeply counterintuitive. One of the first is that moving clocks run slow. A clock carried on a fast-moving spacecraft ticks more slowly than an identical clock left behind on the ground. Not because of any defect in the machinery, but because time itself passes differently for the two. This is not a trick of perception or a philosophical abstraction. It has been measured directly. Take two extremely precise atomic clocks, synchronize them, leave one on the ground, and fly the other around the world in an aircraft. And when they are brought back together, they no longer agree. The traveling clock has fallen behind by exactly the amount the equations predict. The effect is tiny at the speeds aircraft can manage, a matter of fractions of a fraction of a second, but it is real and repeatable, and at higher speeds it grows dramatically. There is an even more constant demonstration humming above your head. The satellites that make up the global positioning system carry atomic clocks, and those clocks move quickly enough and sit high enough above the Earth that time passes measurably differently for them than it does for us on the surface. If the engineers who designed the system had ignored these effects, the position errors would accumulate rapidly, throwing off navigation by a growing margin every day, until the whole system became useless within hours. The fact that satellite navigation works at all, that a device in your pocket can locate you within a few steps, is a continuous, around-the-clock confirmation that time is not the same for everyone. It depends on motion and on position in a gravitational field, exactly as the theory demands. These effects, strange as they are, might still seem to leave the present moment intact. A traveling clock running slow is unsettling, but you can imagine reconciling it with a universal now if you work hard enough. The truly decisive blow lands on a different concept, one even more fundamental to our sense of a shared present. That concept is simultaneity, the idea that two events can happen at the same time. We use it constantly and unconsciously. When you say that something is happening right now on the far side of the planet, or right now on a distant world, you are assuming that the notion of at the same time has a single, definite meaning that everyone shares. Einstein showed that it does not. Whether two separated events happen at the same time is not an absolute fact about the universe. It depends on who is asking, and specifically on how they are moving. There is a classic way to make this vivid, and it repays slow attention. Picture a train moving along a track at high speed, and inside one carriage, exactly at its center, a lamp is switched on. Light spreads out from the lamp in all directions at its fixed speed. There are two doors, one at the front of the carriage and one at the back, each the same distance from the lamp. For a passenger sitting in the middle of the carriage, the situation is perfectly symmetric. The light travels the same distance forward and backward at the same speed, so it reaches the front door and the back door at the same instant. From the passenger's point of view, the two doors are illuminated simultaneously. There is no doubt about it, and any measurement the passenger makes will confirm it. Now, consider someone standing on the platform, watching the same train rush past. For this observer, the light still travels at its fixed speed in both directions, because the speed of light is the same for everyone. But during the time the light is in flight, the train is moving forward. The back door is rushing toward the point where the light was emitted, while the front door is racing away from it. So from the platform observer's perspective, the light has a shorter distance to cover to reach the back door, and a longer distance to reach the front. Since the light moves at the same speed in both directions, it arrives at the back door first, and the front door slightly later. For the person on the platform, the two doors are not illuminated simultaneously. The back one lights up before the front one. Sit with the strangeness of this. Both observers are correct. There is no experiment either could perform that would reveal the other to be mistaken. The passenger genuinely sees the doors light up together. The platform observer genuinely sees them light up one after the other. They are not making errors of measurement or perception. They are reporting accurately on a reality that simply does not have a single answer to the question of whether the two events were simultaneous. Simultaneity, the bedrock of the shared present, turns out to depend entirely on the observer's state of motion. Two events that happen at the same time for one person happen at different times for another, and neither view is privileged over the other. This is the hinge on which everything turns. If different observers slice up the events of the universe into now and not now in different ways, then there is no single, universal present that everyone shares. Your now and the now of someone moving relative to you do not contain the same set of events. And if there is no objective, agreed upon present moment, dividing a settled past from an open future, then the entire intuitive structure of time, the structure built around a single advancing now, loses its foundation. The question becomes unavoidable. If no one can agree on what is happening now across the universe, what does that tell us about whether the past and the future exist? Einstein had shown that the present was relative. The next step would be to ask what kind of reality could possibly accommodate so many different, equally valid presents at once. And the answer would point toward a universe in which all moments exist together. The collapse of a universal present forces a choice, and the choice is sharper than it first appears. If two observers moving relative to one another genuinely disagree about which events are happening now, and if neither of them is wrong, then we have to ask what reality must be like for both of them to be right at the same time. There is a way to picture the answer, and it was given its clearest form not by Einstein himself, but by one of his former teachers, a mathematician named Hermann Minkowski. A few years after the theory of relativity appeared, Minkowski realized that the strange new behavior of space and time made far more sense if you stopped treating them as separate things. Space and time, he argued, were not two distinct stages on which events played out. They were aspects of a single unified structure, and that structure became known as space-time. The idea takes some effort to absorb because we are so accustomed to keeping space and time in separate mental compartments. Space is where things are. Time is when things happen. We move freely through space, walking forward, backward, left, right. But we seem to be carried helplessly through time in one direction at a fixed pace. Minkowski's insight was that this separation is not fundamental. The reason moving clocks run slow, the reason simultaneity depends on the observer, the reason space and time seem to trade off against one another is that they are woven together into a four-dimensional whole. Three of the dimensions are the familiar ones of space. The fourth is time. And every event that ever happens, everything that has occurred or will occur, occupies a definite location in this four-dimensional fabric. To make this concrete, think about how you specify a meeting. You cannot simply tell someone a place. You have to give them a location in space, a building, a floor, a room, and you also have to give them a time, a day, and an hour. Only with all of these together does the meeting have a definite position. 3 numbers fix the place, 1 number fixes the time, and the meeting itself sits at that combination, a single point in the 4-dimensional structure. Minkowski called such a point an event, and the great realization was that the universe could be described as the complete collection of all such events. every meeting, every collision of particles, every heartbeat, every supernova, each one pinned to its own location in spacetime. The history of everything becomes a kind of vast, fixed map. Once you adopt this picture, the puzzle of the disagreeing observers resolves in a remarkable way. The events of the universe are laid out in the four-dimensional structure, complete and unchanging. What differs between observers is not the events themselves, but the way each observer slices the structure into moments. Think of a loaf of bread. The loaf is a single solid object, but you can cut it into slices, and each slice represents everything that exists at one instant, a snapshot of the whole of space at a single time. Now here is the crucial part. An observer at rest cuts the loaf into slices one way, perpendicular to its length, each slice a clean cross-section. An observer in motion cuts the same loaf at a slight angle, producing slices that are tilted relative to the first. Both are slicing the same loaf. Both produce valid slices. But because the cuts are angled differently, a given point in the bread, a given event, falls into different slices depending on who is doing the cutting. This is exactly what is happening with simultaneity. Each observer's now is a slice through space-time, a particular way of selecting which events count as happening at the same time. Observers moving differently slice at different angles, so they sweep up different sets of events into their respective presents. The events themselves do not change. The loaf is the loaf. What changes is only the orientation of the cut. And here lies the heart of the matter, the step that leads directly to eternalism. If the loaf has to be fully present in order for it to be sliced in all these different valid ways, then the entire four-dimensional structure, all of space for all of time, must exist as a complete whole. The past slices and the future slices cannot be less real than the present slice, because one observer's future slice is another observer's present slice, and they are cutting the same loaf. This is the block universe. The name captures the image precisely. The universe is conceived as a single block, four-dimensional, containing every event that has ever happened and will ever happen, all coexisting within the structure. The dinosaurs are still there, located at their position along the time dimension. The reading of these words is there, at a different position. The death of the sun, billions of years from now, is there as well, sitting at its own coordinates. From the perspective of the block, there is no privileged moment that is lit up as the real present, while the others languish in non-existence. Every moment is equally embedded in the structure, equally actual, distinguished only by its position, just as every city on a map is equally real and distinguished only by its location, not by some special status that makes one city exist more than another. The map comparison is worth dwelling on because it clarifies something about the relationship between the block and our experience. When you look at a map of a country, you see all the cities at once, spread out before you. No city is happening now on the map, while the others wait their turn. They simply coexist at different places. Your journey through the country, by contrast, takes you from one city to the next in sequence. At any given moment of your travels, you are in one particular place, and the others lie behind or ahead of you on your route. But the cities you have left behind have not ceased to exist, and the cities ahead are not waiting to be created when you arrive. They are all there, on the map, the whole time. The block universe proposes that time works the same way. Your life is a journey through the four-dimensional structure, and at any point along that journey, you experience one particular moment as your present. But the moments behind you and ahead of you are no less real for being elsewhere. They are simply at different locations in the block. There is a particular feature of an individual's path through the block that physicists find useful, and it deepens the picture. As an object moves through space over time, it traces out a continuous line in space-time, a path that records its position at every instant. This path is called a world line. Your own world line begins at the event of your birth and extends to the event of your death, threading through every place you have ever been and every moment you have ever lived. It is not a thing that grows as you live, with new segments being added at the front edge while old ones fade. In the block picture, your entire world line exists all at once, a single continuous curve laid out in the four-dimensional structure, complete from end to end. The you of childhood and the you of old age are both on that line, both real, both there, separated by distance along the time dimension in just the way two distant points on a road are separated by distance along the ground. It is important to be careful here, because this picture invites a particular kind of confusion. One might object that this is just a mathematical convenience, a way of drawing diagrams, with no claim about what is truly real. Physicists draw all kinds of abstract spaces to help them calculate, and no one thinks those spaces are physically real places. So why should space-time be any different? The answer lies in what the theory of relativity actually requires. The relativity of simultaneity is not a mathematical convenience. It is a tested, measured feature of the world, confirmed by the behavior of clocks and satellites and particles. And the relativity of simultaneity makes very little sense unless the events being sliced in different ways are all genuinely there to be sliced. If the future did not yet exist, then there would be a fact of the matter about which events have happened and which have not, a single objective boundary between the real past and the unreal future. But relativity says there is no such universal boundary, because different observers place the boundary in different places, and all of them are correct. The most natural way to make sense of this is to conclude that there is no boundary at all, that past, present, and future are all equally real, and that the division between them is something observers impose, rather than something the universe contains. This is why the block universe is not merely one philosopher's preference among many. It follows with disturbing directness from physics that has been confirmed countless times. The theory does not force the conclusion with the absolute finality of a mathematical proof, and we will look later at the ways people have tried to resist it. But the pull toward eternalism is strong enough that many physicists regard the block universe as simply the picture that relativity hands us, whether we find it comfortable or not. The flowing present, the vanishing past, the open and unwritten future, all of these begin to look like features of human experience, projected onto a universe that does not actually contain them. And yet, a serious doubt should be nagging at us by now. The argument so far has relied on observers moving relative to one another, and the differences in their slicing have seemed small, the kind of thing that matters for trains and satellites, but hardly touches the grand question of whether the distant past or future is real. If the disagreement about simultaneity were always trivial, one might shrug it off as a technicality, with no real consequences for the existence of other moments. But the disagreement is not always trivial. Push the reasoning far enough, across great distances, and the slicing of two observers can diverge not by fractions of a second, but by years. There is a famous argument that makes this stark, an argument about two people doing nothing more dramatic than strolling past each other on a street, and about how their innocent difference in walking direction can set their definitions of now apart by enormous spans of time across the gulf of space. It is to that argument we turn next. The objection that the slicing differences are too small to matter rests on a hidden assumption, which is that the events we care about are nearby. For events close at hand, the disagreement between observers about what counts as now really is minuscule, far too small to notice in ordinary life. But the geometry of space-time has a feature that amplifies the effect over distance. And once you take that feature seriously, the consequences become difficult to wave away. The argument that brings this out most forcefully was developed by the physicist Roger Penrose, and it has come to be known as the Andromeda paradox, because it concerns our relationship to the Andromeda galaxy, the great spiral of stars that is the nearest large galaxy to our own, and lies an enormous distance away across intergalactic space. The setup could hardly be more ordinary. Imagine two people passing each other on a sidewalk, walking in opposite directions at a normal strolling pace. There is nothing exotic about them. They are not on spaceships, not moving at any appreciable fraction of the speed of light. Just two pedestrians crossing paths on an ordinary street on an ordinary day. At the instant they pass, they are at the same place. But they are moving differently, one heading in one direction and one in the other. And that small difference in motion means they slice space-time at slightly different angles. For nearby events, the resulting disagreement about simultaneity is too tiny to detect. But the tilt of the slice, though small, does not stay small in its effects as you follow it outward. The further away an event is, the more a slight tilt in the slicing plane sweeps across the time dimension. Over the immense distance to the Andromeda galaxy, a tilt produced by walking speed translates into a displacement of days. Here is what that means concretely. Consider the events unfolding in the Andromeda galaxy, so far away that light from it takes a vast stretch of time to reach us. For the pedestrian walking in one direction, the slice of now that passes through their position also passes through a particular moment in Andromeda's history. For the pedestrian walking the other way, the slice of now passes through a different moment in Andromeda's history, displaced from the first by something on the order of a day, possibly more, depending on the exact figures. The two pedestrians are standing in the same spot at the same instant, yet their definitions of what is happening right now in Andromeda differ by a full day or more of that galaxy's history. If something significant were occurring there, the departure of a fleet, the decision of some civilization, an astronomical catastrophe, one pedestrians now might place that event in the future, not yet happened, while the other pedestrians now places it firmly in the past, already over and done. Take a moment to register how strange this is, and how it differs from the train example. With the train, the disagreement about simultaneity concerned events fractions of a second apart, the lighting of two doors. It was real, but it was small. The Andromeda paradox takes the very same principle and stretches it across cosmic distances, and the small disagreement balloons into a difference of days. And the two people producing this enormous divergence are doing nothing more than walking in opposite directions. There is no high speed, no rocket, no extreme physics. The ordinary act of strolling is enough to shift your plane of simultaneity by an amount that, projected across millions of light years, separates one version of now from another by a day of distant history. The effect is built into the geometry of space-time itself, and it appears the moment you accept the constancy of the speed of light and the relativity of simultaneity that follows from it. Now, follow the reasoning to its conclusion, because this is where the paradox earns its weight. If one pedestrians now legitimately includes an event in Andromeda, and the other pedestrians now legitimately excludes it, placing it in the future, then we have to ask whether that event is real. The standard intuition says that the present and the past are real, while the future is not yet real, not yet existent, still open. But if that intuition were correct, then whether the Andromeda event exists would depend on which direction a person on a distant sidewalk happens to be walking. That is plainly absurd. The events in a faraway galaxy cannot possibly depend for their existence on the casual movements of pedestrians who have no causal connection to them whatsoever, and who could not influence them by any means. The galaxy does not check which way people on Earth are walking before deciding whether to exist. So either we accept that reality itself flickers in and out depending on observers, which makes no physical sense, or we accept that the event in Andromeda is simply real, full stop, regardless of how anyone slices their present. And if it is real for the pedestrian who places it in their future, then the future, at least that piece of it, is as real as the past. This is the punch the Andromeda paradox delivers. It takes the abstract claim that the block universe contains all moments and grounds it in a scenario so mundane it is almost comic. Two people walk past each other, and in doing so, they demonstrate that the line between a settled past and an open future cannot be a feature of the universe, because they draw the line in different places, and neither of them is wrong. The only coherent resolution, the one that does not require reality to depend on pedestrian traffic, is that all the events are there, the whole block, and the assignment of any given event to past, present, or future is a perspective rather than a fact about existence. It is worth heading off a tempting misunderstanding at this point, because it is the one most people reach for when they first encounter this argument. The misunderstanding is to think that the pedestrians could somehow see different things, that one of them could observe the Andromeda event while the other could not. That is not what is being claimed, and it is important to be precise. Neither pedestrian can actually see the current state of Andromeda at all, because the light carrying that information has not yet arrived and will not arrive for an enormous span of time. What they disagree about is not what they observe, but what is happening now in their respective definitions of simultaneity at a place they cannot yet see. The paradox is not about perception. It is about the structure of the present moment as defined by the geometry of space-time. The events in Andromeda are causally cut off from the pedestrians, utterly beyond their influence and beyond their sight. And yet, the question of whether those events belong to now still receives two different and equally valid answers. That is precisely why the conclusion is so forceful. The disagreement cannot be resolved by any observation, because it is not about observation. It is about the nature of time itself. There is a subtlety here that deepens the point, rather than weakening it. One might wonder whether the pedestrians could ever come into conflict, whether their disagreement could produce a contradiction, since one of them thinks an event has happened, and the other thinks it has not. The answer is that they can never come into conflict, and the reason illuminates something profound about the structure of space-time. The events about which they disagree are always events that lie beyond any possibility of communication, events so far away that no signal, not even light, could travel between them and the pedestrians in the time available. Relativity is exquisitely careful about this. It allows observers to disagree about the simultaneity of distant events, but only for events that are causally disconnected, events that cannot influence one another. Whenever two events could possibly affect one another, when a signal could pass from one to the other, all observers agree on their order without exception. The disagreement is confined precisely to the region where it can never cause a paradox, where no observer could ever use it to send a message into their own past or learn the outcome of something before it could reach them. The structure protects causality with perfect precision, allowing the relativity of now exactly where it does no harm and forbidding it everywhere it would. This careful structure is not an accident or a patch. It falls out of the geometry naturally, and it points toward the next piece of the picture. The reason some events are forever causally cut off from one another, while others are bound together in a fixed order that everyone agrees on, comes down to the way signals can travel through space-time and the absolute limit imposed by the speed of light. There is a precise geometric object that encodes this limit, that divides for any given event the set of things it could possibly affect from the set of things forever beyond its reach. Understanding that object, the way it carves space-time into regions of possible influence and permanent separation, is the key to seeing why the block universe holds together as a coherent whole rather than dissolving into contradiction. And it reveals something equally important about the past, about the sense in which what has already happened remains anchored in the structure, fixed and unalterable, available in principle to anyone who could reach the right region of space-time. The geometry that protects causality is the same geometry that preserves the past. The object that governs all of this is built from light, and it has a shape worth picturing carefully. Take any single event in space-time, any point with a definite place and a definite time. Call it here and now. From that point, imagine a flash of light expanding outward in all directions. As time passes, the flash forms an ever-growing sphere, racing away at the speed of light. If you track that expanding sphere through space-time, plotting how its radius grows with time, it traces out a cone shape opening toward the future. This is the future light cone of the event, and it represents the boundary of everything that the event could possibly influence. Nothing travels faster than light, so any effect radiating from here and now must stay within or on that expanding cone. Events inside the future light cone can be reached by a signal from the original event. Events outside it cannot be reached by any means, no matter how the signal is sent. There is a mirror image pointing the other way. Imagine all the flashes of light from the past that could have converged on here and now, arriving precisely at this point. They form a cone opening toward the past light cone, and it represents everything that could possibly have influenced the event. Anything that has affected you at this moment, any light reaching your eyes, any sound reaching your ears, any force acting on your body, must have come from within your past light cone. Together, the two cones, one opening to the future and one to the past, divide all of space-time into distinct regions with sharply different relationships to the event at their apex. There is the future the event can affect, the past that could have affected it, and a vast region outside both cones, the elsewhere, consisting of events too far away in space and too close in time to have any causal connection to the event at all. This structure of cones is the reason the relativity of simultaneity never produces a contradiction. The events about which different observers disagree, the ones swept into one observer's now and out of another's, always lie in the elsewhere, outside both light cones. They are causally disconnected from the observer by definition, too distant to send or receive any signal in the time available. The Andromeda events that the two pedestrians disputed lie in their elsewhere, beyond reach, which is exactly why the pedestrians can disagree about them without any possibility of conflict. By contrast, any two events linked by light cones, where one lies inside the other's cone, have a fixed order that every observer agrees on without exception. If event A is inside the past light cone of event B, then A happened before B for everyone, in every state of motion, without any ambiguity at all. The light cone structure enforces a universal agreement on causal order, while permitting disagreement only in the region where it can do no harm. This is the deep reason the block universe is internally consistent. The geometry separates what must be agreed upon from what may be disputed, and it does so with absolute precision. Once you see space-time in terms of light cones, the past takes on a particular character that is central to the question we are pursuing. The past, in this picture, is not a region that has been deleted or overwritten. It is a definite, fixed part of the structure, anchored by the unanimous agreement of all observers about causal order. Every event in your past light cone happened, in a sense that no observer can dispute, no matter how they move. The light from those events is still propagating outward through the universe, still carrying the information about what occurred. When you look up at the night sky, you are not seeing the stars as they are now. You are looking directly into the past light cone of this moment, seeing each star as it was when the light left it, some of that light having traveled for thousands of years, some for millions. The past is not gone. It is laid out behind you in the structure, and its light is still in transit, still reaching new places, still real. Consider what astronomy actually does, because it makes the persistence of the past tangible rather than abstract. Every telescope is, in effect, a device for looking backward in time. When astronomers point their instruments at a galaxy 100 million light-years away, they are observing that galaxy as it existed 100 million years ago, because that is how long the light has been traveling to reach them. The galaxy they see may have changed enormously since then. Its stars may have aged, exploded, rearranged themselves entirely. But the image arriving now is a faithful record of a past state, preserved in the light and delivered intact across an enormous gulf of space and time. The deeper into space we look, the further back in time we see, until at the limit we observe light from the early universe itself, radiation that has been traveling almost since the beginning. The past is not an abstraction inferred from memory. It is physically present, encoded in light that fills the universe, available to anyone with the instruments to capture it. This is where the Eternalist reading gains real traction, because it suggests that the past is not merely remembered or recorded, but is, in the fullest sense, still there. Think about the light from your 10th birthday. The photons that bounced off the cake, off the faces of the people around you, off your own younger self, did not vanish. They left the room, passed through any windows, and if nothing absorbed them, they continued outward into space at the speed of light. Right now, that light is somewhere out in the cosmos, a sphere of information about that exact moment, expanding ever outward, a few light years from Earth by now, and growing more distant with every passing second. In a quite literal sense, the visual record of your 10th birthday is still propagating through the universe, still carrying the arrangement of that scene, still available in principle to any observer in the right place to intercept it. The moment has not been erased. It has only moved away. This observation invites a thought that sounds like fantasy, but follows directly from the physics. If the light from past events is still traveling outward, then an observer far enough away, intercepting that light at the right time, would see those events unfolding as if they were happening now. An observer 10 light years from Earth, with a powerful enough telescope, would right now be seeing events on Earth from 10 years ago, watching them play out in real time from their perspective. An observer 100 light years away would be watching events from a century ago. The past is not only preserved, it is observable perpetually by anyone positioned to catch the light as it passes. There is no single moment at which the past stops being available. It is always available somewhere, to someone in the right location, because the light carrying it never stops moving outward through the block. We have to be careful, though, not to overstate what this allows. Seeing the past is not the same as reaching it or changing it. The light cone structure that lets a distant observer see Earth's past also forbids them from doing anything about it. By the time the light reaches them, the events are far outside their past light cone in the relevant sense, already determined, already a fixed part of the structure. They can witness, but they cannot intervene. The information flows outward at the speed of light, and no faster, and nothing can outrun it to alter what has already occurred. The past is observable but sealed, visible but untouchable. This combination, that the past is real and persistent, and even watchable, yet completely fixed and beyond alteration, is exactly what the block universe predicts. The events are there, embedded in the structure, neither erased nor editable. There is a measurable phenomenon that makes the permanence of the past even more vivid, and it has to do with the largest scales we can observe. The light from the most distant objects in the universe has been traveling for so long that the universe itself has expanded substantially during the journey. This expansion stretches the light, shifting it toward longer wavelengths, toward the red end of the spectrum, a phenomenon called redshift. By measuring how much a galaxy's light has been stretched, astronomers can determine how long it has been traveling, and therefore how far into the past they are looking. The redshift is a direct, quantitative measure of distance into the past, a way of reading the depth of time written into the light itself. The further the light has come, the more it has been stretched, and the older the image it carries. This is not metaphor. It is a measurement performed routinely, a precise reading of how deeply a given beam of light penetrates back into the history of the block. So the past, far from being a vanished ghost, emerges from this analysis as a structurally permanent feature of reality, anchored by the unanimous causal ordering that light cones enforce, physically preserved in light that continues to propagate, and even directly observable to anyone positioned to receive that light. The case for the reality of the past begins to feel almost overwhelming. But the block universe makes a far bolder claim than this. And it is here that the intellectual difficulty sharpens considerably. The same reasoning that establishes the reality of the past, the same relativity of simultaneity, the same Andromeda argument, the same geometry of slicing, applies with exactly equal force to the future. If the past is real because all moments coexist in the block, then the future must be real for precisely the same reason. And a real future, a future that already exists in full detail, raises questions about choice and possibility that are far harder to face than the persistence of what has already happened. If tomorrow is already there in the structure, waiting at its coordinates exactly as yesterday sits at its own, then what becomes of the open future we believe we are walking into? The reality of the past is unsettling but bearable, because the past is already fixed in our intuition anyway. We do not expect to change what has happened, so a model that makes the past permanent merely confirms something we already accept. The future is a different matter entirely. Everything in our experience tells us that the future is open, unwritten, a realm of possibility that we shape through our choices. We deliberate, we decide, we act, and we feel that in doing so, we are bringing one of many possible futures into being, while the others fall away unrealized. The block universe challenges this directly. If all moments coexist in the four-dimensional structure, and if the future is simply the set of moments located at later positions along the time dimension, then the future already exists, in complete and specific detail, exactly as the past does. Tomorrow is already there. Next year is already there. The day of your death is already there, sitting at its coordinates, as real and as fixed as the day of your birth. The argument for this is not separate from the argument for the reality of the past. It is the very same argument, and that is what makes it so hard to escape. Recall the relativity of simultaneity. One observer's present slice through spacetime is another observer's future slice. When the two pedestrians passed each other, one of them placed a certain Andromeda event in the present or past, while the other placed it in the future. And we concluded that the event had to be real regardless, because its existence could not depend on which way someone was walking. But notice what that conclusion commits us to. The event was in someone's future. We declared it real anyway. We therefore declared a future event to be real. There is no way to accept the reasoning that establishes the reality of the past while rejecting the reality of the future, because the reasoning does not distinguish between them. The slicing argument treats all directions through the block identically. Whatever reality the past has, the future has in equal measure. This is the point at which many people want to get off the train, and it is worth taking their resistance seriously rather than brushing it aside. The objection usually takes the form of an appeal to free will. Surely the objection goes, "I have not yet decided what I will have for breakfast tomorrow. The decision lies ahead of me. How can the outcome already exist when I have not yet made the choice that determines it?" If tomorrow's breakfast is already sitting in the block, then my sense of deciding is a sham, and my deliberation is an empty performance whose result was fixed all along. The block universe on this reading seems to drain all genuine agency out of life, reducing us to passengers on a train whose route was laid down before we ever boarded. The Eternalist response to this is subtle, and it does not simply dismiss the worry. It reframes what a decision is. In the block picture, your decision tomorrow about breakfast is a real event, located at its place in the structure. It is not bypassed or rendered fake by the fact that it already exists in the block. It is a genuine part of the process by which that region of spacetime takes the form it has. The choice is not skipped over. It happens fully, with all the deliberation and weighing of options that you experience. The block does not contain the outcome without the choosing. It contains the choosing and the outcome together, woven into the same fabric, because the choosing is part of how the outcome comes to be what it is. Your deliberation is not an illusion masking a predetermined result. Your deliberation is itself one of the events embedded in the structure, a real link in the chain, no less real for being already located in the block. This is admittedly hard to hold in the mind, because our intuition insists that for a choice to be real, the future must be open at the moment of choosing, with genuinely available alternatives that could still go either way. The block universe suggests instead that the openness we feel is a feature of our limited vantage point rather than a feature of reality. From inside your world line, moving along it, you do not know what lies ahead. The future is hidden from you, screened off by the simple fact that the information about later events has not yet reached you and cannot reach you until you arrive there. This epistemic openness, this not knowing, is entirely real. You genuinely do not know what you will choose, and your deliberation is the process by which you come to know it, by which you arrive at the choice. But epistemic openness is not the same as the future not existing. The far side of a mountain exists, even though you cannot see it from where you stand. The future, on this view, is like the far side of the mountain, hidden from your current position, but already there. There is a useful comparison with the way we already think about the past in this respect. You do not feel that the past threatens your free will, even though the past is fixed and unchangeable. The decisions you made yesterday are now settled, located in the block, beyond alteration. Yet you do not conclude from this that yesterday's choices were not really choices, that your deliberation yesterday was a sham. You accept that they were genuine decisions, made freely as you experienced them, and that they are now fixed precisely because they have been made. The Eternalist asks you to extend the same understanding to the future. Tomorrow's choices are fixed in the block in the same way yesterday's are, but they are fixed as choices, as the outcomes of real deliberation, not as outcomes imposed from outside that bypass your agency. The difference between past and future on this view is not that one is fixed and the other open. Both are fixed. The difference is only that you have access to information about one and not the other, because of your position in the structure and the direction in which information flows. It is worth pausing on a distinction that often gets blurred here, the distinction between determinism and eternalism, because they are frequently confused and they are not the same thing. Determinism is the claim that the state of the universe at one time, together with the laws of physics, completely fixes the state at all later times, so that the future follows necessarily from the past, like the next step in a calculation. Eternalism is the claim that all moments exist. These are logically independent. You could have a deterministic block, where each slice follows rigidly from the previous one. But you could also have a block that includes genuine randomness, where the laws do not uniquely determine later slices from earlier ones, and yet all the slices still exist, including whatever the random outcomes turned out to be. The block universe does not by itself require that the future be calculable from the present. It requires only that the future be real. Whether the universe is also deterministic is a separate question, and as we will see when we turn to quantum mechanics, there are reasons to think it may not be, even though the block may still contain all moments. The future can be both real and, in a certain sense, not predetermined, if the events that fill it include outcomes that were not fixed in advance by anything earlier. This opens a strange possibility worth stating plainly. The block universe is compatible with a future that exists, but was not bound to be exactly as it is by the past. The block simply contains whatever happens, including whatever turns out to be the case in situations where the outcome was genuinely open in the sense of not being forced by prior conditions. What it rules out is not the openness of outcomes, but the non-existence of the future. The future is there. How it came to take the particular form it has, whether by strict necessity or with an element of irreducible chance, is a further question that the block picture leaves room for either way. This is why the Eternalist need not be a fatalist in the crude sense. They are not committed to the idea that the future is sealed by the past and that nothing you do matters. They are committed only to the idea that the future, including everything you do and the difference it makes, already exists as part of the complete structure. Still, even granting all of this, a persistent discomfort remains, and it is the right discomfort to have at this stage. If every moment of my life already exists, fixed in the block, then in some sense the whole of my life is already complete, already laid out from birth to death, and I am merely traversing it, experiencing one slice at a time while believing I am building something new. The feeling of moving through time, of the present advancing and the future arriving, would then be exactly that, a feeling, a feature of consciousness rather than of the world. And this brings us to a question we have so far set aside, but can no longer avoid. If the universe does not actually flow, if all moments simply exist together with no objective passage from one to the next, then why do we experience time as flowing so powerfully and so undeniably? Why does the present feel like it is moving if, in the structure of reality, nothing is moving at all? The answer cannot lie in the physics of the block, because the block contains no flow. It must lie somewhere else, in the nature of the experiencer, in the way a mind embedded in the structure comes to feel a current that the structure itself does not contain. If the block universe is correct, then the most vivid feature of our experience, the relentless sense that time is passing, has no counterpart in the structure of reality. This is a genuinely difficult situation, because the passage of time does not feel like an interpretation or a theory. It feels like the most basic fact of existence, more certain than anything we could learn from physics. We do not infer that time is passing the way we infer the existence of atoms. We seem to feel it directly, continuously, in every waking moment. Any account that calls this feeling an illusion owes us an explanation of where the feeling comes from, because simply declaring it illusory is not enough. We need to understand how a mind embedded in a static four-dimensional structure would come to have such a powerful and persistent impression of flow. The answer turns out to lie in the architecture of memory and the way the brain constructs its model of the world. Begin with what flow actually consists of in experience. When you say that time is passing, what are you actually noticing? You are noticing that the present moment is different from the moment before, that things have changed, that what was anticipated has become what is happening and is becoming what has happened. But notice how much of this depends on memory. You know that time has passed because you remember the previous state and can compare it to the current one. Without memory, there would be no sense of passage at all, only an isolated instant with nothing to measure it against. The feeling of flow is fundamentally a feeling of accumulation, of a growing store of memories, of a present that is continuously enriched by comparison with a remembered past. And memory, crucially, has a direction built into it. You remember the past but not the future. This asymmetry is the engine of the felt flow of time. Consider what this means in the context of the block. At each point along your world line, your brain is in a particular physical state, and that state includes memories, records of earlier points along the world line, encoded in the structure of your neurons. At a point corresponding to this afternoon, your brain contains memories of this morning. At a point corresponding to this morning, your brain contains memories of last night, but none of this afternoon, because this afternoon lies in a direction along the world line from which no information has reached that earlier brain state. Each slice of you, each momentary configuration of your brain, carries within it a record of the slices that lie in one direction along your world line, and no record of the slices that lie in the other. From the inside, this looks exactly like a past you can remember, and a future you cannot. The asymmetry of memory, present at every point in the block, generates at every point the impression of a fixed past and an open future, even though both directions are equally real and equally fixed in the structure. This is a subtle and important point, so it is worth restating from a slightly different angle. In the block universe, there is no single moving observer who travels along the world line, accumulating experiences. Instead, there is a whole world line, every point of which contains a complete momentary experience, including whatever memories are appropriate to that point. The you of this morning is having the experience of this morning, complete with memories of last night, right there at that location in the block, permanently. The you of this afternoon is having the experience of this afternoon, complete with memories of this morning, right there at that location, permanently. There is no need for anything to move or flow. Each momentary self simply exists at its location, equipped with the memories that the structure provides, and each one feels itself to be the present, the leading edge of an advancing now, because each one has memories of earlier states and none of later ones. The sense of being a single self moving through time is assembled from this chain of momentary selves, each linked to the previous by memory, like frames of a film that, viewed in sequence, produce the impression of continuous motion that is not present in any single frame. The film analogy returns here with real force, and it is worth developing carefully because it captures something essential. A strip of film consists of many still images, each one frozen and unchanging. There is no motion in any individual frame. Yet when the frames are presented in rapid succession, the viewer experiences smooth, continuous motion. Where does that motion come from? Not from the film, which is static. It comes from the viewer's perceptual system, which takes the sequence of stills and constructs from them, the experience of movement. The motion is real as an experience, but it is not a property of the film. The block universe proposes that the flow of time is exactly analogous. The block is the film, a static collection of frozen moments. Consciousness, moving from frame to frame in the sense that each momentary conscious state succeeds the previous along the world line, constructs from this sequence the experience of flowing time. The flow is real as an experience, but it is not a property of the universe. But the analogy has a limit that we must be honest about, and confronting it deepens the puzzle, rather than resolving it cheaply. In the case of the film, there is an actual projector running the frames past a light, and there is a viewer sitting in time, watching the film unfold in their own present moment. The motion of the film through the projector is a real process happening in time. But in the case of the block universe, there is no external projector and no external time in which the block is being played. The block is all of time. There is nothing outside it running it forward. So we cannot say that consciousness moves through the block the way a film moves through a projector, because that would require a second time, a meta-time, in which the movement through the block occurs, and that just pushes the problem back a level. The flow of time cannot be explained by positing a flow of consciousness through the block, because that flow would itself need explaining in the same terms. This is one of the genuinely hard problems in this area, and it would be dishonest to pretend it has a tidy solution. The most careful version of the Eternalist answer does not posit any movement at all. It says that there is no flow, full stop. Not even a flow of consciousness through the block. There is only the static structure, and within it, at each point along each world line, a momentary conscious state that has a certain character. Part of that character is the impression of flow. Each momentary state, by virtue of containing memories of earlier states and anticipations of later ones, by virtue of representing itself as the present moment, poised between a remembered past and an anticipated future, has built into it the feeling of being a moment in a flowing stream of time. The flow is not something that happens between moments. It is a quality contained within each moment, a way each momentary experience represents its own situation. There is no need for a sequence to be played, because each frame already contains in itself the impression of being part of a moving sequence. The feeling of flow is local to each moment, manufactured fresh at every point, requiring no actual motion anywhere. This is a strange and demanding idea, and most people find it difficult to accept on first encounter, which is entirely reasonable. It asks us to believe that our most immediate experience, the passage of time, is systematically misleading about the nature of reality. But this would not be the first time that immediate experience proved misleading about deep structure. Our immediate experience tells us that the ground beneath us is still, and the sun moves across the sky, when in fact the earth is spinning at enormous speed and hurtling around the sun. Our immediate experience tells us that a table is solid and continuous, when in fact it is mostly empty space populated by particles bound by forces. Our immediate experience tells us that up and down are absolute directions, when in fact they are merely the local direction of gravity, pointing different ways for people on opposite sides of the planet. In each case, the way things seem to us, shaped by our particular situation and the particular way our perception works, turns out to diverge sharply from the way things are. The passage of time may be the deepest and most stubborn example of this pattern, an appearance so woven into consciousness that we mistake it for the bedrock of reality. There is even some support for this view from the study of how the brain handles time, because it turns out that our perception of time is far more constructed and malleable than the smooth flow we seem to experience. The brain does not have a single clock that ticks off uniform moments. Instead, it assembles the sense of time from many different processes, and these can be manipulated and can come apart. Time seems to slow during moments of intense fear or focus, when the brain processes information more densely. Time seems to compress in memory when a period contained little that was novel. The brain stitches together events that arrive through different senses at different speeds, sound and light and touch, and presents them as a single synchronized moment, hiding the underlying delays. It even, in certain experimental conditions, appears to assign events to the wrong order, constructing a sequence after the fact rather than reading it off directly. All of this suggests that the experienced flow of time is a model the brain builds, a representation it constructs for its own purposes, rather than a direct perception of an external flowing. And if the flow is a construction, then the absence of flow in the underlying physics is no longer a contradiction. The brain builds the river. The universe is the unmoving landscape through which the brain represents itself as traveling. Yet even if we grant that the felt flow of time is a construction of the mind, a deep puzzle remains unsolved, and it concerns not our experience, but the physics itself. For there is one place where the laws of nature do seem to care about the direction of time, one phenomenon that stubbornly distinguishes past from future in a way that the block picture must somehow accommodate. Heat flows from hot to cold, and never the reverse. Eggs break, but never unbreak. The disorder of the universe relentlessly increases. If the underlying laws are blind to the direction of time, and if all moments exist equally in the block, then why does the world contain this powerful, universal arrow, pointing relentlessly from past to future? Why does so much of physics run only one way, if time itself does not flow at all? The arrow of time is the sharpest challenge to the idea that the past and future are symmetric, equally real directions through an unchanging block. Everywhere we look, the world seems to distinguish past from future in an obvious and irreversible way. Drop a glass and it shatters into fragments, but you will never see the fragments leap up and reassemble into a glass. Stir cream into coffee and it disperses into a uniform brown, but it will never spontaneously separate back into white cream and black coffee. A hot cup left on a table cools to room temperature, but a room temperature cup never spontaneously heats itself by drawing warmth from the air. In each case, there is a clear before and a clear after, and the process runs only one way. This one-way character is so pervasive that it seems to define the very difference between past and future. The past is the direction in which the glass was whole. The future is the direction in which it lies in pieces. The puzzle deepens enormously when you examine the underlying laws that govern the particles making up the glass, the coffee, the cup. Those laws, the fundamental rules describing how matter and energy behave at the smallest scales, are very nearly symmetric in time. If you took a film of two particles colliding and bouncing apart, then ran the film backward, the reversed film would also show a physically valid collision, one that obeys all the same laws. At the level of individual particles, there is almost nothing to distinguish forward from backward. The laws work equally well in both directions. So we face a genuine paradox. The microscopic laws do not care about the direction of time, yet the macroscopic world is full of processes that run only one way. Where does the arrow come from, if not from the fundamental laws? How does a one-way world emerge from two-way rules? The answer, worked out over the course of the 19th and 20th centuries, lies in the concept of entropy and in the statistical behavior of enormous numbers of particles. Entropy is, roughly speaking, a measure of disorder, but it is more precise and more illuminating to think of it in terms of arrangements. Consider the broken glass. There is essentially only one way, or a very small number of ways, for the particles to be arranged so as to form an intact glass standing on the table. But there are an astronomically large number of ways for those same particles to be arranged as scattered fragments on the floor. The intact configuration is special, rare, highly ordered. The shattered configurations are common, abundant, disordered. Entropy counts these arrangements. Low entropy means few possible arrangements consistent with the overall appearance. High entropy means many. And the central insight is that systems evolve from less probable arrangements to more probable ones simply because there are vastly more ways to be disordered than to be ordered. Picture it this way. Imagine a deck of cards arranged in perfect order, all the suits together and each suit in sequence. There is exactly one such arrangement. Now shuffle the deck. After shuffling, the cards are almost certainly in some disordered sequence, because there are an enormous number of disordered sequences and only one ordered one. Shuffle again and again, and you will essentially never recover the ordered arrangement by chance, not because any law forbids it, but because it is so vastly outnumbered by the disordered possibilities. The deck drifts toward disorder, not because disorder is favored by any force, but because disorder is simply far more common among the possible arrangements. The glass shatters and does not reassemble for the same reason. The scattered arrangement is overwhelmingly more probable than the assembled one, so the system moves toward scattering and stays there. This is the second law of thermodynamics, the principle that the entropy of an isolated system tends to increase. And it is the origin of the arrow of time we observe in everyday processes. Notice something crucial about this explanation. It does not come from any asymmetry in the laws themselves. The laws remain time-symmetric. The arrow emerges purely from probability, from the overwhelming numerical dominance of disordered arrangements over ordered ones. The reason we see entropy increase toward the future and not toward the past is, in a sense, a statistical near certainty rather than an absolute law. It would not be strictly impossible for the broken glass to reassemble. It would merely require the particles to find their way, by chance, into one of the vanishingly rare arrangements that constitute an intact glass. And the odds against this are so staggering that it never happens in the entire history of the universe. The arrow of time, then, is statistical. It points in the direction of increasing entropy, because increasing entropy is overwhelmingly probable, not because the laws forbid the reverse. But this raises a profound and still partly unresolved question, one that takes us to the edge of current understanding. If entropy increases toward the future because disordered states are more probable, then by the same reasoning, entropy should increase toward the past as well, because the same probabilistic argument runs in both directions. Take any moderately ordered state and ask what is most probable in either temporal direction, and the statistics say disorder in both. Yet when we look toward the past, we do not find higher entropy. We find lower entropy. The past was more ordered than the present, not less. The glass was whole. The cream was separate. Yesterday was more ordered than today, and the day before more ordered still, all the way back. This means that the universe must have begun in an extraordinarily ordered, extraordinarily low entropy state, and that all the entropy increase we observe is the universe relaxing from that special beginning toward greater disorder. The arrow of time, on this account, points away from a low entropy past, and that low entropy past is a condition we have to assume rather than something the statistical argument explains. This special initial condition is one of the great open problems in physics, and it is sometimes called the past hypothesis. Why did the universe begin in such an ordered, low entropy state? The statistical argument explains why entropy increases once you have a low entropy starting point, but it does not explain why there was a low entropy starting point to begin with. A truly random beginning would have been high entropy, disordered, and from such a beginning there would be no arrow of time at all, only featureless uniformity in both directions. The fact that the universe started ordered and has been increasing in entropy ever since is a fact about initial conditions that current physics describes but does not fully account for. The arrow of time, the most obvious asymmetry in our experience, traces back ultimately to a mysterious feature of the universe's beginning, a beginning of remarkably low entropy, whose origin remains genuinely unknown. What does all of this mean for the block universe and the reality of the past and future? It means that the arrow of time, far from contradicting the block, is entirely compatible with it, and in fact, fits it rather naturally. The block universe contains all moments, laid out in the four-dimensional structure, with no objective flow from one to the next. But the block has a particular character along the time dimension. At one end, the end we call the past, entropy is low. At the other end, the end we call the future, entropy is high. The entropy gradient is a feature of the contents of the block, a way the block is organized along its temporal extent, like a gradient of color across a painting that is itself entirely static. The arrow of time is not a flow. It is a direction in the block along which the contents become more disordered. We experience this gradient as the passage of time because, as we saw, our memories and our very capacity to think and record depend on entropy increase. And so our sense of moving from past to future is really a reflection of our position along the entropy gradient within the static structure. This connects back to the puzzle of why we remember the past and not the future, and it ties the threads together in a satisfying way. Memory is a physical process. To form a memory is to create a record, an ordered correlation between the state of your brain and some event in the world. Creating such a record requires, by the laws of thermodynamics, an increase in entropy elsewhere, a dissipation of energy, an irreversible step. Memory formation runs in the direction of increasing entropy. This is why we can have records of the low entropy direction, the past, but not of the high entropy direction, the future. Records point back toward order, toward the special initial condition, because record formation itself depends on the entropy gradient. The reason the past is fixed and rememberable, while the future is unknown, is at bottom the same reason the glass shatters and does not reassemble. It is the entropy gradient, the slope of disorder across the block, that gives time its felt direction and gives memory its orientation. The block does not flow. It is merely lopsided, ordered at one end and disordered at the other. And we, embedded within it and built from irreversible processes, experience that lopsidedness as the relentless forward march of time. So the arrow of time, which seemed to threaten the symmetric block, turns out to be a feature of the block's contents rather than evidence of an objective flow. The asymmetry is real, but it is an asymmetry in how things are arranged along the time dimension, not an asymmetry in which moments exist. All moments exist equally. They simply differ in their entropy, and that difference, refracted through the physics of memory and perception, produces the powerful impression that time is moving. Yet even as this account holds together at the level of large objects and statistical ensembles, a different and arguably deeper challenge waits at the smallest scale of reality. For when we descend into the quantum world, the world of individual particles and their strange behavior, the clean picture of a fixed four-dimensional structure begins to encounter complications that physicists have not fully resolved. There, the very question of whether the future is determined, and even whether events have definite values before they are observed, reopens in ways that bear directly on whether the block can truly contain all moments laid out in advance. Everything we have considered so far rests on the framework of relativity, which describes a smooth, continuous space-time in which events have definite locations and the block is laid out in full. But relativity is not the only pillar of modern physics. The other is quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales, and it paints a picture of reality that sits uneasily with the clean, fully specified block. Quantum mechanics introduces genuine uncertainty, not merely uncertainty in our knowledge, but apparently uncertainty in the world itself, and it raises the possibility that events do not have definite values until they are observed or measured. If that is true, then the idea of a future already laid out in complete detail becomes harder to maintain, because there may be no complete detail to lay out until measurement brings it into being. The tension between these two great theories lies at the heart of the deepest unresolved questions in physics, and it bears directly on whether the past and future can really exist in the full sense the block requires. To see the difficulty, consider one of the central features of quantum mechanics, the description of a particle by something called a wave function. Before you measure a property of a particle, such as its position, the wave function does not assign it a single definite value. Instead, it assigns a spread of possibilities, each with a certain likelihood. The particle is described as being, in some sense, in a combination of many possible states at once, a situation called superposition. It is not that the particle has a definite position that we happen not to know. The mathematics strongly suggests that the particle genuinely does not have a single definite position until a measurement is made. Only upon measurement does the wave function appear to collapse, selecting one outcome from the spread of possibilities, and the particle acquires a definite value. Before measurement, possibilities. After measurement, a single actuality. This is the quantum measurement problem, and it is one of the most puzzling features of the theory. The relevance to the block universe is immediate. In the relativistic block, every event has a definite character. The particle is at a definite location. The field has a definite value. Everything is specified throughout the four-dimensional structure. But quantum mechanics seems to say that before measurement, there is no definite value, only a spread of possibilities. If the future contains measurements that have not yet been made, then the outcomes of those measurements are not yet definite, and the block would seem to be incomplete in those regions, filled not with actualities, but with possibilities awaiting resolution. This is the crux of the tension. A future that exists in full detail seems to require definite values everywhere, but quantum mechanics seems to deny definite values until measurement, which suggests the future is genuinely open and undetermined until the moments arrive. There are, however, Several ways physicists have tried to reconcile these pictures, and each one casts the question of the block in a different light. The differences among them are not minor technical details. They represent genuinely different proposals about what reality is, and which one is correct remains unknown. We have to walk through the main options carefully, because the fate of the block universe depends substantially on which of them turns out to be true, and because each one is internally coherent enough to be taken seriously. The first option takes quantum uncertainty at face value and concludes that the future is genuinely open. On this view, the collapse of the wave function is a real physical process, a moment at which the universe selects one outcome from many, and the others cease to be possibilities. If collapse is real, then the future is not laid out in advance, because the outcomes of future measurements do not yet exist as definite facts. They will be determined when the measurements occur, and not before. This would seem to undermine the full block universe, replacing it with a picture in which the past is fixed and definite, but the future is a realm of genuine possibility that becomes actual moment by moment as collapses occur. Some have called this a growing block, a structure in which the past is real and settled. The present is the leading edge where possibility crystallizes into actuality, and the future does not yet exist. The growing block preserves much of the eternalist insight about the reality of the past while restoring an open future, and it appeals to those who find the fully fixed block hard to swallow. But it faces a serious problem of its own, which is that the relativity of simultaneity makes the notion of a single objective present, a single leading edge where collapse happens, very difficult to define. If there is no universal now, then there is no universal boundary at which the growing block stops growing and the picture begins to fragment. The second option avoids collapse altogether, and in doing so restores the full block in a startling way. On this view, the wave function never collapses. All the possibilities in the superposition are equally real, and when a measurement occurs, rather than selecting one outcome, the universe in effect divides, with each possible outcome realized in its own branch. This is the many worlds interpretation, and it proposes that reality is constantly splitting into a vast and ever-growing tree of branches, each one a fully real world in which a different outcome occurred. On this account, there is no genuine indeterminacy in the universe as a whole. Every possible outcome happens, each in its own branch. The future is not open in the sense of being undetermined. It is fixed in the sense that all outcomes occur. The block universe is preserved and even expanded, because now it contains not a single history, but the entire branching structure of all possible histories, every one of them real, every one of them laid out in full. The uncertainty we experience is then merely uncertainty about which branch we will find ourselves in, not uncertainty about what exists. Everything that can happen does happen somewhere in the structure. The many worlds picture is, in a sense, the most thoroughly eternalist of all the options, because it makes even the apparent openness of quantum outcomes into a fully real, fully existing structure. Nothing is left undetermined or unrealized. The price, of course, is the staggering proliferation of worlds, a tree of branches multiplying at every quantum event throughout the entire universe, an ontology of almost unimaginable extravagance. Many physicists find this price too high to pay. Others argue that it is simply what the mathematics says, if you take it seriously and refuse to add an extra collapse process by hand. The debate remains unsettled, and it is worth being honest that no experiment has yet distinguished between these interpretations, because they make the same predictions for what any observer will see. The disagreement is about what reality is, not about what we will measure, and that makes it extraordinarily difficult to resolve. A third option preserves definite values throughout, including in the past and arguably the future, by proposing that particles always have definite positions, guided by the wave function, but never lacking a specific location. On this view, sometimes associated with the physicist David Bohm, the apparent indeterminacy of quantum mechanics is, like the indeterminacy of a coin toss, a matter of our ignorance rather than the world's lack of definiteness. The particle always has a definite position. We simply do not know it until we measure, but it was there all along, determined by factors we cannot fully access. This restores a kind of determinism and a kind of definiteness compatible with a full block, though it does so at the cost of introducing influences that propagate in ways that sit awkwardly with relativity. Here again we see the recurring theme. Restoring the clean block in one respect tends to strain the relationship with relativity in another. The two great theories pull against each other, and every attempt to reconcile them pays a price somewhere. What emerges from surveying these options is not a clean answer, but a clarification of what is at stake. Whether the future exists in full detail depends on which interpretation of quantum mechanics is correct, and that question is genuinely open. If the wave function collapses, and collapse is a real, objective, indeterministic process, then perhaps the future is not laid out in advance, and the block is incomplete toward the future, even if the past is fixed. If there is no collapse and all branches are real, then the block is not only complete, but vastly larger than we imagined, containing every possible history. If particles have definite positions all along, then the block may be complete and even deterministic. The relativistic argument for the block universe is powerful and rests on well-tested physics, but quantum mechanics complicates the picture in ways that prevent us from declaring the matter settled. The honest position is that the reality of the future, in the full eternalist sense, remains entangled with the unresolved foundations of quantum theory. There is one further consideration that draws relativity and quantum mechanics together in a suggestive way, and it concerns whether collapse can even be made consistent with relativity at all. If collapse is a real process that happens at a definite moment, selecting an outcome across space instantaneously, then it seems to require exactly the kind of universal present that relativity denies. For collapse to happen now, everywhere at once, there would have to be a fact about what now means across all of space, and relativity tells us there is no such fact. This is a serious obstacle for any interpretation that relies on objective collapse, and it is one reason some physicists are drawn to the no-collapse pictures, which fit more comfortably with the relativistic block. The very feature of relativity that drove us toward eternalism, the relativity of simultaneity, also pushes against the idea of an objective collapse that would restore an open future. The two great theories taken together may lean more toward the full block than either does alone, though the matter is far from decided, and the deepest reconciliation of relativity and quantum mechanics remains unknown. Even setting aside these interpretive disputes, there is something striking in how observation and measurement seem to occupy a special role in quantum mechanics. a role that touches directly on the relationship between the observer and the structure of reality. The act of measurement, whatever it ultimately turns out to be, appears to be the moment at which possibility becomes actuality, at which the spread of the wave function gives way to a single value. If the block universe is correct and all moments exist, then every measurement that ever occurs is itself an event located in the block, and the puzzle becomes how to understand the relationship between the definite outcomes recorded in the structure and the indefinite possibilities that quantum mechanics assigns before measurement. This is the measurement puzzle in its sharpest form, and it leads us to examine more closely what observation actually does, and what it might mean for a universe that may be laid out all at once, yet seems to crystallize into definiteness only when something looks. The role of observation in quantum mechanics has been a source of confusion and even mysticism, and it is worth approaching it carefully, stripping away the misunderstandings to see what the physics actually requires and what it leaves open. The basic fact is this: when a quantum system is not being measured, it evolves smoothly and predictably according to a well-defined equation, spreading out into superpositions of possibilities. But when a measurement is made, what we observe is always a single definite outcome, never a superposition. We never see a particle in two places at once. We see it here, or we see it there. The transition from the smooth spread of possibilities to the single observed outcome is the measurement puzzle, and the word observation has caused enormous trouble because it suggests that consciousness, the act of a mind taking notice, plays some special role in bringing reality into definite form. It is important to be clear that the mainstream of physics does not hold that consciousness causes the outcome. The word measurement in quantum mechanics refers to any interaction in which the quantum system becomes correlated with a large complex system, the kind of system that contains enormous numbers of particles, whether that system is a laboratory instrument, a speck of dust, or the air in a room. The special role is played not by minds, but by the boundary between the small, isolated quantum world and the large, messy, macroscopic world. When a particle in superposition interacts with a large system, the superposition spreads into that system and rapidly becomes entangled with countless degrees of freedom, a process called decoherence. Decoherence does not, strictly speaking, collapse the superposition, but it makes the different possibilities effectively independent, no longer able to interfere with one another, so that for all practical purposes, the system behaves as though it has settled into one definite outcome. The appearance of a single definite world emerges from the way quantum systems lose their delicate coherence when they interact with the vast complexity of their surroundings. This connects to the block universe in an interesting way. In the block, every measurement, every act of decoherence, every interaction between a quantum system and its environment is an event located in the four-dimensional structure. The records produced by these measurements, the definite outcomes registered in instruments and brains, are written into the block at their respective locations. From within the block, looking along a world line, one finds a consistent sequence of definite measurement outcomes, each recorded in the appropriate place, each correlated with the records that come before it along the entropy gradient. The puzzle of why we see definite outcomes rather than superpositions becomes, in this framing, a question about the structure of the records embedded in the block and the way decoherence organizes them. The block contains a consistent web of definite records, and any observer threading through it experiences a coherent, single-valued history, regardless of whatever superpositions exist at the level of the underlying wave function. But this raises a question that returns us to the deepest issue: the relationship between the static, fully laid out structure and the apparent process by which possibilities become actualities. If the block is complete, containing all events at all times, then in what sense does anything ever become definite? Becoming, after all, implies a transition, a moment at which something that was not settled becomes settled. And the block does not seem to allow for transitions, since all moments simply exist. The eternalist answer, consistent with everything we have built so far, is that there is no becoming in the objective sense, only the appearance of becoming generated by the structure of records along each world line. At each point in the block, the records of earlier measurements are definite, fixed, settled, while the outcomes of later measurements are not yet recorded at that point, and so appear, from that vantage, to be open and undetermined. The feeling that a measurement outcome becomes definite when it is made is, once again, a feature of the observer's position in the structure, not a feature of the structure itself. The outcome is definite in the block at its location. It only seems to become definite because from earlier points along the world line, there is no record of it yet. This is a demanding idea, and it is worth dwelling on what it implies. It implies that even quantum measurement, which feels like the very paradigm of an open future crystallizing into a settled past, can be understood as a static pattern of records in a block that does not change. The crystallization is apparent, not real. Every measurement outcome that will ever be recorded is already located in the block at its proper place, definite and fixed, just as every past outcome is. What distinguishes them from any given vantage is only whether a record of them has yet been formed at that vantage. And record formation, as we saw, runs along the entropy gradient. So the apparent flow of quantum becoming, like the apparent flow of time itself, reduces to the structure of records and the asymmetry of memory within an unchanging four-dimensional whole. The same explanation that accounted for the felt passage of time accounts for the felt crystallization of quantum possibility. Both are perspectival effects generated within the block, requiring no actual change in the block. There is, however, a genuine subtlety that we should not paper over, and it concerns whether the block can really be said to contain definite values everywhere, or whether it contains in some regions only the spread of possibilities described by the wave function. If the no-collapse picture is correct, then what the block contains is not a single definite history, but the full branching structure of the wave function, with all outcomes realized in their respective branches. In that case, the block is definite, but only when you include all the branches. Within any single branch, threading through one consistent history, an observer finds definite outcomes everywhere, but the totality contains all branches at once. If, on the other hand, an objective collapse picture is correct, then the block would contain genuinely definite single outcomes, but at the cost of a collapse process that strains against relativity, as we discussed. The shape of the block, whether it is a single definite history or a vast branching tree, depends on the resolution of the quantum measurement problem, which remains unsettled. What does not depend on that resolution is the eternalist conclusion that, whatever the block contains, it contains it timelessly, without objective flow, with all moments coexisting. This survey of measurement and observation, then, does not overturn the block universe so much as reveal its flexibility and its dependence on deep, open questions. The block can accommodate definite outcomes or branching possibilities. It can absorb the appearance of quantum becoming into the same perspectival framework that absorbed the passage of time. What it cannot easily do is restore an objective, universal, flowing present, at which possibilities collapse into actualities everywhere at once, because relativity forbids the universal present that such a process would require. The convergence of the two great theories, difficult as their full reconciliation remains, seems to push consistently away from objective flow and toward a structure laid out in its entirety. However, we ultimately understand its quantum contents. Having pressed this far into the foundations, it is natural to ask whether any of this could ever connect to something exotic, something that would let the block's permanence of the past become more than an abstract claim. If every moment exists, and if the past is a fixed and permanent part of the structure, the imagination reaches naturally toward the question of whether the structure could ever fold back on itself, whether the geometry of space-time might permit paths that return to earlier regions, paths that would turn the abstract permanence of the past into something potentially reachable. This is not idle fantasy. The equations of general relativity, the theory of gravity that describes how space-time curves and bends in the presence of matter and energy, contains solutions in which the geometry does strange things, in which the smooth, simple structure we have assumed gives way to twisted configurations where the very notions of past and future become tangled. Exploring those solutions takes us to the strangest territory in all of physics, where the block universe meets the possibility of loops in time itself. General relativity, Einstein's theory of gravity, describes space-time not as a fixed stage, but as a flexible fabric that bends and curves in response to matter and energy. Mass tells space-time how to curve, and the curvature of space-time tells matter how to move. This is how gravity works in the theory. It is not a force pulling objects together across space, but a curvature of the space-time structure itself, so that objects following the straightest possible paths through curved space-time appear to be drawn toward massive bodies. The theory has passed every experimental test with remarkable precision, predicting the bending of light by the sun, the slowing of clocks in gravitational fields, the existence of black holes, and the ripples in space-time called gravitational waves that have now been detected directly. It is one of the most successful theories in the history of science, and buried within its equations are solutions that describe space-times far stranger than the smooth, well-behaved structure we have been assuming. In the ordinary space-time of everyday experience, the light cones we discussed earlier are arranged in an orderly way. At every point, the future light cone opens consistently toward the future, and as you move from point to point, the cones tilt smoothly, but never so drastically that the future of one point loops back into the past of another. This orderly arrangement is what guarantees that cause precedes effect everywhere, that the causal structure is consistent, that you cannot influence your own past. But general relativity does not require this orderly arrangement in every possible space-time. In regions of extreme curvature, where matter and energy are arranged in particular extreme ways, the light cones can tilt so severely that they begin to lean over, and in certain solutions they tilt so far that following the future direction long enough brings you back to your starting point. A path that always moves into the local future can, if the cones are tilted enough along the way, form a closed loop, returning to an earlier event. Such a path is called a closed, time-like curve, and its existence in the mathematics of general relativity is one of the most provocative features of the theory. The first such solution was discovered by the mathematician Kurt Gödel, a close friend of Einstein, who found that a universe rotating as a whole would contain closed time-like curves. In Gödel's rotating universe, the cumulative tilting of light cones around the rotation would allow a traveler, always moving forward in their own local time, to eventually arrive back at an event in their own past. This was not a flaw in Gödel's mathematics. It was a genuine solution to Einstein's equations, a possible configuration of spacetime that the theory permits. Einstein himself found the result deeply troubling, because it seemed to allow, at least in principle, for a kind of journey into the past, and that threatened the entire causal structure on which physics seemed to depend. Other solutions with similar features have since been found, involving rotating black holes, hypothetical tunnels through spacetime called wormholes, and configurations of exotic matter with unusual properties. In each case, the geometry of spacetime curves so severely that the clean distinction between past and future, which we have relied on throughout, breaks down in localized regions. What is striking about closed time-like curves in relation to the block universe is how naturally they fit in one sense, and how severely they challenge it in another. They fit naturally because the block universe is, by its nature, a structure in which all events coexist. If the past is a permanent part of the structure, then a path that loops back to an earlier region is not reaching a vanished past, but simply traversing a different part of the existing block, arriving at a region that was always there. The block has no difficulty accommodating loops because it does not depend on a flowing present that would be contradicted by returning to an earlier time. The events on the loop simply exist, arranged in a closed configuration rather than an open line. In a block universe, a closed time-like curve is just a particular shape of world line, one that closes on itself rather than extending from a birth to a death. There is nothing incoherent about a closed loop in a structure where all events coexist timelessly. The severe challenge comes from the question of consistency, from the famous puzzles that arise when one imagines using such a loop to influence the past. If you could travel along a closed time-like curve back to an earlier event, could you change what happened there? The block universe gives a clear answer, and it is an answer that dissolves the paradoxes rather than indulging them. You cannot change the past because the past is a fixed part of the structure, already containing whatever you did when you arrived there. If a traveler journeys around a closed time-like curve and arrives at an earlier event, then the traveler's presence and actions at that earlier event are already part of the block, already woven into what happened there. The traveler does not change the past. The traveler was always part of the past they arrive at. There is only one history, one block, and it includes the loop and everything the traveler does on it, consistently, with no contradiction. The events around the loop must be self-consistent, fitting together into a single coherent structure, because there is only one structure, and it either contains a consistent set of events, or it is not a valid solution at all. This requirement of self-consistency is sometimes stated as a principle, the idea that the only journeys around closed time-like curves that can occur are those that are fully consistent with the history they are part of. A traveler cannot do anything that would prevent the very journey they are on, because if they did, the journey would not have happened, and the contradiction would mean the configuration is not a valid solution. The block universe enforces consistency automatically, because it admits only complete, coherent structures. There is no separate first version of history that gets overwritten by a second version after the traveler interferes. There is only the one block, containing the loop and all its events in a single, consistent whole. The classic paradoxes in which a traveler prevents their own journey simply cannot arise in a block universe, because such a scenario would not correspond to any consistent structure and therefore would not be a possible history at all. It must be emphasized that all of this remains highly speculative as a matter of physical reality, however solid it is as mathematics. The solutions to Einstein's equations that contain closed time-like curves require conditions that may not exist anywhere in the actual universe. Gödel's rotating universe does not match our own, which does not appear to rotate in the required way. The wormhole solutions require forms of exotic matter with negative energy density that may not exist in the quantities needed, or at all. Many physicists suspect that some deeper principle, perhaps emerging from a full theory combining gravity and quantum mechanics, forbids the formation of closed time-like curves in practice, even though the equations of classical general relativity permit them. There is a conjecture, advanced by Stephen Hawking, that the laws of physics conspire to prevent the formation of closed time-like curves, protecting the consistency of history by some mechanism we do not yet fully understand. Whether such a protection mechanism exists is unknown, and it touches on the unresolved frontier where relativity and quantum theory meet. But the mere mathematical possibility of closed time-like curves is significant for our investigation, because it demonstrates that the structure of space-time, as described by our best theory of gravity, does not inherently forbid connections between different times. The block universe, in its general relativistic form, is a structure rich enough to contain loops, tunnels, and exotic geometries in which the relationships among events become far more intricate than a simple progression from past to future. And this richness reinforces the central theme. The past, in such a structure, is not a region that has ceased to exist and become inaccessible in principle. It is a permanent part of the geometry, and in certain extreme configurations, the geometry itself provides paths back to it. The permanence of the past, which we established through the relativity of simultaneity and the persistence of light, takes on an even more concrete character when we consider that the curved space-time of general relativity could, under the right conditions, fold the past and the present into direct geometric contact. This naturally raises the question of whether anything less exotic than a closed, time-like curve could let us reach toward the past. Whether there is any way, short of bending space-time into loops, that the permanent past might leave traces we could detect or signals we could receive. We have already seen that the light from past events continues to propagate outward, carrying information about what occurred, observable in principle to anyone in the right location. The question now becomes whether this persistence of information could ever be more than a one-way record receding into the distance, whether the structure of the block, with its permanent past and its propagating light, might allow for echoes, traces, or signals that reach across time in ways we could actually observe and measure. If the past truly still exists, the natural human impulse is to ask whether we could ever touch it, hear it, or detect it, and that impulse leads to a careful examination of what the physics actually permits. If the past genuinely persists as a permanent feature of the block, the most natural question a curious mind can ask is whether we could ever detect it, whether any signal, trace, or echo from what has already happened could reach us in a form we could measure. The answer, carefully considered, is both more encouraging and more restrictive than one might hope, and the boundary between what is possible and what is forbidden traces exactly the structure of light cones we examined earlier. We can detect the past in one specific and profound sense, and we are forbidden from detecting it in another, and understanding which is which reveals a great deal about the kind of universe we inhabit. Begin with the sense in which detecting the past is not only possible, but constant and unavoidable. Everything you observe is, strictly speaking, in the past. The light from this page or screen left it a tiny fraction of a second ago. The light from the sun left it about 8 minutes ago, so that we never see the sun as it is now, but always as it was 8 minutes earlier. The light from the nearest star beyond the sun has traveled for several years. The light from distant galaxies has traveled for millions or billions of years. Every observation reaches into the past light cone, retrieving information about events that have already occurred. In this sense, the entire enterprise of astronomy is the detection of the past, the systematic gathering of ancient light to reconstruct what happened long ago and far away. When astronomers observe a supernova in a distant galaxy, they are watching a star explode in an event that, from our perspective, happened millions of years before any human existed. Yet the light arrives now, fresh, carrying its information intact across the vast gulf of space and time. The past is not merely inferred. It is directly observed continuously every time we open our eyes or point a telescope at the sky. The deepest reach of this backward observation extends almost to the beginning of the universe itself. There exists a faint glow of radiation that fills all of space, detectable in every direction, the cosmic microwave background. This radiation was released when the universe was very young, when it first became transparent to light, and it has been traveling ever since, gradually stretched and cooled by the expansion of the universe, until it now appears as a faint microwave glow. When we detect this radiation, we are observing the universe as it was in its infancy, capturing light that has been in transit for almost the entire history of the cosmos. The cosmic microwave background is, in a precise sense, an image of the distant past, a snapshot of an early era preserved in light and delivered to our instruments across an enormous span of time. The fact that we can detect it at all is a direct demonstration that the past leaves real, measurable traces that persist and propagate, available to anyone with the means to capture them. Beyond light, there are other channels through which the past reaches us. Gravitational waves, the ripples in space-time predicted by general relativity, and now detected directly, carry information about violent events such as the collision of black holes, events that occurred long ago and far away. When these waves are detected, they convey the signature of a catastrophic merger that happened, in some cases, more than 1 billion years before the signal arrived. Neutrinos, the ghostly particles that pass through matter almost without interacting, also stream toward us from past events, from the cores of distant stars, and from the early universe, carrying information that light cannot. Each of these channels is another window onto the persistent past, another way the structure of the block delivers its earlier regions to our instruments in the present. The past is not silent. It speaks to us constantly, in light, in gravitational waves, in particles, in every signal that has been traveling toward us since the events that produced it. But there is a strict limit to all of this, and the limit is essential to understanding the kind of access we have. We can receive information from the past, but we cannot send information to it, and we cannot interact with it. The light from a distant supernova reaches us, but we cannot reach back to the supernova. The cosmic microwave background arrives at our detectors, but we cannot influence the early universe that emitted it. All of this detection is strictly one way, governed by the light cone structure that allows information to flow from the past into our present, but never from our present into the past. We are receivers of the past, not participants in it. The events we observe are sealed, fixed, beyond our influence, exactly as the block universe predicts. We can witness the past in extraordinary detail, but we can do nothing to change it, because by the time its light reaches us, it lies outside any region we could affect. The asymmetry is total. Information flows toward us from earlier events along the entropy gradient, and never the reverse. This brings us to a more speculative question, one that lies at the edge of what physics can address. Could there be, somewhere in the structure of the block, a way to access the past more directly than through the receding light it emits? We have already seen that the exotic geometries of general relativity, the closed time-like curves, would in principle provide such access, folding the past and present into direct contact, though they remain speculative and may be forbidden by some deeper principle. Short of such extreme geometries, the answer appears to be no. The ordinary structure of spacetime, the well-behaved structure in which we actually find ourselves, permits only the one-way reception of past information through propagating signals. The past is real, permanent, and observable, but it is not reachable. It exists, but at a distance we cannot cross, separated from us by the rigid causal structure that forbids backward influence. There is, however, a subtle and beautiful sense in which the past is more present than we usually realize, and it has to do with the way information about earlier states is encoded in the present arrangement of matter. The universe around you is, in a sense, a vast record of its own past. The light from ancient events still propagates through it. The arrangement of galaxies preserves the imprint of conditions in the early universe. The composition of matter, the abundance of different elements, records the nuclear processes that occurred in the first moments of the cosmos and in the cores of stars that died long ago. The very atoms in your body were forged in stellar furnaces and scattered by explosions that happened billions of years ago. In this sense, the past is not only observable through incoming light, but is physically embodied in the present structure of everything that exists. The present is, in part, a frozen record of the past, a configuration shaped by everything that came before, and preserving, in its details, the traces of that history. The block universe makes this vivid. The earlier regions of the block are connected to the later regions by the continuous propagation of light and the conservation of matter and energy, so that each later slice carries forward the imprint of the slices before it. This understanding reframes what it means to say the past still exists. It is not merely that there is a region of the block, far away along the time dimension, where past events sit frozen, inaccessible. It is that those past events are continuously connected to the present through the propagation of their effects, through the light they emitted, the matter they shaped, the structures they left behind. The past reaches into the present, not as a vanished cause whose effects have faded, but as an ongoing presence, woven into everything we observe and everything we are. When you look at the night sky and see ancient light, when you hold matter forged in dead stars, when you detect the faint glow of the early universe, you are in direct contact with the past, not metaphorically but physically, through signals and structures that have persisted across enormous spans of time. The permanence of the past in the block is not an abstract claim about distant frozen regions. It is a fact embodied in the light and matter that surround you at every moment. And yet, for all this contact, the past remains beyond our intervention, witnessed but unalterable, present but sealed. This combination of intimate connection and absolute inaccessibility is the precise character that the block universe assigns to the past, and it carries implications that reach beyond physics into the deepest questions of human existence. For if every moment of a life permanently exists, connected to every other moment through the structure of the block, then the meaning of memory, of loss, and of death itself must be reconsidered. The events of a life on this view are not erased by their passing, but remain forever fixed in the structure, real and complete. What this means for how we understand a human life, lived within a universe that does not erase its moments, but preserves them all, is a question that the physics opens but cannot fully answer, and it deserves careful and honest examination. If every moment of a life permanently exists, fixed in the structure of the block, then the most familiar facts of human existence appear in a different light. We are accustomed to thinking of a life as something that passes, that unfolds, and is consumed in the unfolding, each moment spent and gone the instant it is lived. Childhood is over. Past relationships have ended. People we have lost are gone. This is the ordinary understanding of a life, and it carries with it a particular kind of sorrow, the sorrow of impermanence, the sense that everything we experience is slipping away, even as we live it, vanishing into a past that no longer exists. The block universe challenges this understanding at its root. If eternalism is correct, then no moment of your life is ever lost. Childhood is not over in the sense of having ceased to exist. It is located at its position in the block, permanent and complete, exactly as real as this moment. Every experience you have ever had remains fixed in the structure, neither erased nor diminished by the fact that you are no longer there to experience it from your current vantage. Consider what this means for memory and loss. When we lose someone, we feel that they have ceased to exist, that the person who was once here is now simply gone, present only in our recollection. The block universe offers a strikingly different picture. The person who has died has not been erased from reality. Their life, every moment of it, remains permanently located in the block, from their birth to their death, a complete and unalterable world line, embedded in the four-dimensional structure. The conversations you had with them, the time you spent together, the entirety of their existence, all of it remains real, fixed at its coordinates, as actual as any present moment. They are not here in your current slice of the block, in the region you are now traversing, but they are not nowhere. They are elsewhere in the structure, at their own location, living their life exactly as they did, permanently. In the block universe, the dead are not annihilated. They are simply located at times we have moved past, in regions of the structure we can no longer reach, but which exist nonetheless with full reality. This is a genuinely different way of understanding loss, and it is important not to overstate the comfort it offers or to misrepresent what it actually claims. It does not mean that the dead continue to have new experiences, that they go on living in some hidden realm, or that we will be reunited with them in any ordinary sense. The block universe is not a theory of an afterlife, and it would be a distortion to present it as one. What it claims is more austere and, in its way, more profound. It claims that the moments of a life once lived are permanent features of reality, not erased by their passing. The person who lived those moments lived them, fully and really, and that living is a permanent fact, written indelibly into the structure of the universe. Their existence is not undone by their death. It remains fixed and complete at its place in the block. Whether this offers consolation is a personal matter, but it is at least a different relationship to loss than the one we usually assume, in which the past is annihilated and only memory remains as a fading trace. The same reframing applies to your own life and to the prospect of your own death. We tend to regard death as a kind of erasure, a point at which we cease to exist, and after which there is nothing. The block universe complicates this in a specific way. Your death is an event located in the block, at the end of your world line. After that point, along the time dimension, you are not present. But this does not erase the life that came before. Your entire existence, from birth to death, remains permanently embedded in the structure. You will always have existed, in the strong sense that the moments of your life are eternal features of reality, never undone. The block does not offer continued experience beyond death, for the world line simply ends, but it offers a kind of permanence to everything that came before, a guarantee that what was lived is never unlived, that the reality of your existence is not contingent on your continuing to be present in later slices of the structure. You are, in the block, a permanent part of the universe, located in a particular span of its time dimension, complete and real, forever. There is a striking observation that follows from the asymmetry of memory we discussed earlier, and it bears on how this permanence is experienced from the inside. At every moment of your life, located at its place in the block, you are having that experience, complete with the memories appropriate to that point, and the sense of being present in a flowing now. The you of your 10th birthday is, at that location in the block, experiencing that birthday permanently. The you of this moment is, at this location, experiencing this moment permanently. There is no single traveling self that has moved past the birthday and left it behind. There is, rather, a whole succession of momentary selves, each one located at its point along the world line, each one experiencing its moment as the present. From within the block, every moment of your life is, in a sense, always happening, always being experienced at its location, never fading into a past that has stopped occurring. The fading we feel, the sense that the birthday is over and gone, is a feature of our current vantage, of the fact that the present self has memories of the birthday, but the birthday self had no memories of now. But the birthday is not over in the structure. It is occurring eternally at its place in the block, just as this moment is occurring at its place. This is a subtle point and easy to misunderstand, so it deserves careful statement. The claim is not that you are consciously experiencing all moments of your life simultaneously, in some expanded awareness that takes in your whole existence at once. From within any single moment, you experience only that moment, with its particular memories, and its particular sense of now. The claim is rather about the structure of reality, that each of these moments is permanently real, each one the seat of its own experience, all of them coexisting in the block, without any of them being privileged as the one true present. The flow that would carry you out of the birthday and into the present and onward toward death is, as we have seen, not a feature of the structure, but a feature of how each momentary self represents its own situation. In the structure, all your moments simply are, each one alive at its location, each one as real as any other. What does this do to the way we might think about a human life as a whole? It suggests that a life is not a process of accumulation and loss, in which experiences are gathered and then surrendered, but a complete and permanent object, a world line extending through the block from beginning to end, every part of it equally real. The shape of that world line, the experiences along it, the relationships it formed, the things it accomplished, are fixed features of the universe, not transient events that flicker into existence and out again. There is a way of seeing this that lessens the grip of impermanence, that resists the feeling that everything is slipping away. Nothing is slipping away. Everything that happens is permanent. The moments we live become, the instant they are lived, eternal parts of the structure of reality, beyond the reach of erasure. The sorrow of impermanence on this view rests on a misunderstanding, on the projection of a flow that the universe does not contain, onto a structure that actually preserves everything it holds. But honesty requires acknowledging the other face of this permanence, because it is not entirely consoling. If every moment is permanent, then so are the moments of suffering, the mistakes, the pain. The block does not selectively preserve the good and erase the bad. It preserves everything, fixed and unalterable. The worst moments of a life are as permanent as the best, and the fixedness of the future, which we examined earlier, carries its own weight. If the future already exists, then the difficulties ahead, the losses still to come, the eventual death, are all already there, fixed in the structure, as real as the past. This is not an easy thought, and it would be dishonest to present the block universe as offering only comfort. It offers rather a particular and demanding way of understanding existence, one in which everything is permanent, the joy and the suffering alike, the beginning and the end alike, all of it fixed in a structure that does not flow and does not change. Whether this is a source of consolation or of unease depends on how one holds it, and on which aspect of the permanence one chooses to dwell upon. There is one further consideration that softens the starkness somewhat, and it returns us to the relationship between the structure and our experience of it. Although the block contains all moments, including the difficult ones, we never experience them all at once, never have to bear the whole weight of a life simultaneously. From within the structure, we experience one moment at a time, each with its own texture, and the difficult moments are bounded, located, finite in their extent along the world line, surrounded by other moments of a different character. The permanence of a hard moment does not mean it is endlessly suffered. It means it is real at its location, occurring there, but it does not spread to fill the whole of the structure. Each moment keeps its place. And the same is true of the good moments, which retain their reality at their locations, permanent and complete, available in the structure, even when we have moved, in our experience, far beyond them. The block holds everything in its place, the difficult and the joyful alike, each one eternal, each one bounded, each one a permanent part of the whole that a life amounts to. These reflections take us to the boundary of what physics can say, into territory where the science opens questions it cannot itself answer, questions about meaning and value, and how to live within a universe of this kind. The physics establishes the structure. It tells us that all moments may coexist, that the past persists, that the future is fixed, that the flow we feel is generated within us rather than found in the world. What we make of this, how we choose to understand a human life lived within such a structure, is not something the equations can settle. But the physics does something valuable even here. It removes a particular assumption we rarely examine, the assumption that the past is simply gone, that what has happened has ceased to be, that impermanence is the final truth of existence. In its place, it offers the possibility that nothing is ever lost, that every moment endures, that the universe is a structure that preserves rather than erases. And with that possibility in view, we can return one last time to the central question, gathering everything we have examined into a single picture of what time might actually be, and of whether the river we feel ourselves carried along truly flows at all, at